rubber infill and a low level of compaction. The second surface we used was termed the low traction surface. So this reduced the traction by 6.2%, and it consisted of medium fiber length, low fiber density, TPE infill material, and a low level of compaction. And the third we termed the high traction surface. So it increased traction 8.3%, had a medium fiber length, high fiber density, rubber infill, and a high amount of compaction. So for biomechanical testing, we had 16 male athletes come to the lab, and they performed maximal effort beat cut movements on each of the different surfaces. So we used our motion capture system, so high-speed camera and force plate, and we attached markers to the shank, the rear foot, and the forefoot, and we calculated the joint kinematics and kinetics at the knee and ankle joint. So we rigidly mounted each of the 3 different artificial turf surfaces to the force platform, and we used a paired t-test to compare the low and high surfaces to the control only. And our main variable of interest was the non-sagittal plane joint moments, as previous studies have shown that these are related to joint loading as well as joint injury. So first, looking at the results at the ankle joint. So here we have the ankle transverse plane moment as a function of the stance space during the cut. So the green line is the low traction surface, black line is the control, and the red line is the high traction surface. So if we isolate and just look at that peak external rotation moment, we got a significant reduction in the low traction surface compared to the control, and there was a significant increase in that moment in the high traction surface compared to the control. Moving on to the frontal plane ankle joint moments as a function of the stance space during the cut. Again, isolating that peak eversion moment, we can see that when athletes performed on the low traction surface, they significantly reduced that peak moment by about 6.3%. Moving on to the knee joint. So here we have the transverse plane knee joint moment as a function of the stance space, highlighting the peak external rotation moment. There was no differences between any of the surfaces when the athletes cut on the surfaces. And then lastly, looking at the knee frontal plane moment. So specifically that initial peak adduction moment, comparing the low traction to the control, there was no difference. But when we compared the high traction surface to the control, there was a significant increase in that peak moment by about 21%. So an overall summary for this project, we found that components of artificial turf can alter rotational traction. Specifically, increasing the density of the fibers can lead to an increase in traction. Altering the infill material can alter the traction depending on the specific infill. And increasing the compaction or aging of the field can increase the traction as well. So these changes in traction are substantial enough to alter athlete biomechanics. So a low traction surface could potentially reduce injury due to reductions in the ankle transverse plane joint moment and ankle frontal plane joint moment, while a high traction surface could potentially increase injury risk due to increases in the ankle transverse plane joint moment and increases in the knee frontal plane joint moment. So overall, potentially artificial turf does have an advantage over natural grass because it consists of individual components which could be altered and optimized in order to reduce and alter joint moments and kinematics, which could then potentially alter the mechanical properties of the surface in order to lead to a reduction in potentially athlete injury on that surface. Thank you very much.
Thanks a lot. I was wondering if you might have said that, I might have missed it. Did you use an elastic layer in the lab tests with the athletes under the actual turf?
So like a shock pad? No.
Do you think that would maybe change at least the extent of the effects? If the shock pad takes some of the deformation?
Potentially. So for these specific surfaces, they were designed to not have a shock pad. So I don't think in this instance that would apply, but potentially putting a shock pad under the surface could mitigate some of the changes between them.
did you make the mechanical tests for the mechanical traction test? What usually the FIFA does and DIN and EU standard tests are?
Yeah, so this is our own kind of in-house method that we've done previously and in previous papers that we published. That's why we continue to use it. But we know the FIFA test, we just don't utilize it in our lab.
The question I'm asking is because there are thresholds and we don't know how they are related to muscles really loading actually. That's
Sharon Dixon from the University of Exeter. Thank you very much for the presentation, nicely delivered. Would you mind commenting on what effect you think footwear might have? So do you think we'll get the same ordering of these results if you have footwear characteristics?
That's a great question, and I don't know the answer. I think that potentially the ordering would change depending on the footwear. So potentially in the future, in terms of footwear companies, you could optimize your footwear to interact specifically with the specific field that the players are playing on. I think it is the interaction from the shoe and surface, so changing the shoe would change that interaction.
From the James Baldwin University, did you also capture performance variables, meaning that did you get the same performance on the lower traction surface?
So we did not measure performance, so we had them going at their maximal effort. So there could be some differences in performance on the high traction compared with the low traction. We just didn't feel that we had enough space in our lab to actually get a meaningful performance drill or measurement on the surfaces we had, but that definitely could be in.
Thanks for the great presentation. Let's move on to the second presentation. The second presentation is by Ho Jong-gil from Korea National Sport University, South Korea, and his presentation will be on a new approach to quantifying the center of pressure, COP trajectory using a shoelace formula as a potential measure of movement control during walking around.
Thanks for the introduction. Hello everyone, my name is Ho Jong-gil from Korea National Sports University. I'm very honored to be here because this is my first time. So I hope you enjoy it. Okay, so the title of my talk is A New Approach to Quantify the Center of Pressure Trajectory Using a Shoelace Formula as a Potential Measure of Movement Control during walking and running. Center of pressure is an instantaneous point location of the ground reaction force. With COP can provide useful information to characterize human movement. It may be related to the function of motion or the effects of the shoes. COP trajectory has been used in the recent biomechanics studies. Studies have tried to differentiate the types of foot shape and joint disease during walking or heel strike patterns during running by the observation of COP shape. The observation often includes the analysis of the location and direction of COP path or variability of COP location with respect to the reference line. In biomechanics, plantar pressure device is often used in the lab because of several benefits. In general, plantar pressure device can provide peak pressure during gait, and this pressure also can be divided into a few areas of the foot. COP is also one of the variables which can be measured by the plantar pressure device. However, current COP analysis has a major limitation of quantifying COP path, especially biomechanics studies using the analysis of COP trajectory often face the difficulties in the analysis of the shape or pattern should pass between the individuals. This is the should path from one single stride during walking. If we added more than one stride should lines, they never perfectly overlapped. And then it creates the area by short lines. This area by the multiple short lines can represent some kind of characteristic of human movement. If the area of short lines is relatively smaller in a certain individual compared with others, we can say her or his short pattern is consistent. It can be also used as some indication of the stability of movement pattern. Therefore, the purpose of this study was to determine movement and speed effects on the area of short trajectory during walking and running. 36 male filter runners were recruited for this study. The same normal running shoes for each subject was provided Villa Amendele, Korea. The shoe coordinates were obtained at each stance using the PEDAX system with a sampling of 100 Hz. In order to calculate the area of multiple shoe paths, we used the shoelace formula, a mathematical algorithm used to calculate the area of the simple polygon. When we use a shoelace formula, we also needed to select the point of the outside of shoe point using the algorithm by Graham's scan. The procedure of the selection of the point, it starts from the lowest point to the second point by searching every possible angles and select the smallest angle with respect to the reference line. You can see slide. Each subject performed treadmill, walking and running at 3 different speeds. Each subject was given 5 minutes free walking time to adjust, and then they were collected with 2 minutes. So 2 minutes of walking or running, and a 5 minutes break between each speed. The area of all shopping points from 10 strides was calculated for each subject, and then averaged for each speed. Here are the results of the area between the 3 conditions. There are significant differences in the area between 1.3 meter for walking and 3.5 meter per second running, and 1.3 meter per second walking, and 4.5 per second running. However, there is a tendency to decrease in the area of shopping points in 4.5 meter per second running compared with 3.5 per second walking, but it was not statistically significant. Then we also conducted a validation of study using a force plate because of lower frequency and accuracy of plantar pressure device. One virtual runner participated in this validation with the same walking and running speed. In order to match the shopping point from the force plate with respect to the shoe, 2 reflecting markers on the toe and heel of the shoe were placed. The first graph, actual trajectory of shopping path from 10 trials of running using a force plate. Then, its shopping line was repositioned to the point of heel marker of the shoes, as you can see in the second graph. Finally, each toe marker of the shoe was matched by vector transformation in third graph. there is a comparison of COP paths between three different conditions. Based on the analysis from PostGRED, there are differences in the area existing between the conditions. When we look at details in the shape and area, the shape was similar between pentafacial device and PostGRED, but the area calculated and collected by using a PostGRED was larger compared with a pentafacial device. So, to our knowledge, this is the first study to quantify the area of COP trajectory by using Dulles formula in human motion. Both systems successfully differentiate movement patterns between walking and running. However, the analysis of COP paths from a PostGRED seems to be more sensitive because of high sampling frequency. Finally, we carefully suggest that this new approach to quantify COP trajectory can be used as an objective analysis of the function of human movement for its applications such as the shoes or orthotape in biomechanics research. For future direction of our study, we will collect the data of pentafacial and extreme treatment and then compare between two measurement effects at the same time. Also, we have a plan to correlate the area of COP with other biomechanical variables such as 3D joint angles and moments. We would like to acknowledge the support from the lab at the university and Philip Global for their financial support. Thank you.
Thank you very much for the presentation. Thank you. The paper is now open for questions.
Thank you for the presentations, Mario from France. And if I understood well, you in your area you put all the COP trajectory. How do you manage for outliers or steps that are really different from others in your method? If there is one step really different from the other, because you can ensure that the people always do the same. Do you take it into account in your area?
You can measure exactly.
We had a request if one of the other authors can help with the answers here because of the language, so thank you.
Yeah, thank you. Yeah, as a co-author of this project, if you allow, I'd like to answer. So, great question actually. So, if there are outliers, so one single trial is off from the main, the mean, maybe that's why we still improve some calculation process, how we account for the density of the COP points. But this is a kind of initial work, how we're going to get the new ideas to analyze the shape of the COP. Yeah. Thank you. Yeah.
Any further questions?
Matt, University of Southern California. So this center of pressure area has been used to in a study that looking at the posture control in older adults. So can you, because when you're presenting, I'm thinking how can we apply this knowledge into maybe product, or what's the rationale behind looking at center of pressure area as opposed to center of pressure geometry?
measure is very useful for shoes development and missions. I think yes, the development shoes is a useful factor because this area is related to stability and really anchor joint and medial lateral direction.
We have time for one more question. If not, I'd like to thank you for the presentation. The next talk is by Stefan Silverson. I'd like to ask him up on stage. Stefan will be presenting on the potential of foot-mounted 3D accelerometers to predict lower extremity loading in running.
Thank you Tony for the introduction. I think that all of us here in this room agree that loading variables determined in running from, for example, ground reaction forces, free moments, joint moments, or even more sophisticated from muscle modeling are important in order to understand the relationship between running, tissue adaptation or injury, and in the end, injury risk. Still, we need relatively sophisticated equipment to perform these analyses and calculate them, which makes them lab-based. It doesn't really allow us to acknowledge real-world running conditions, and they only deliver us snapshot results for one period in time. And it's also tough to address fatigue effects in it. And that makes, at least in my opinion, us hard to identify the precise cause-effect relationships between those loading variables and running injuries. For example, if you consider the classical prospective study design, then you have an initial data collection at one snapshot in time, and then you have a follow-up period where you hope that your subjects are actually getting injured. And these injuries are related to certain risk factors, which can be biomechanical factors that can be addressed or affected by footwear design, but it is also caused by, for example, training errors, other everyday activities or nutrition or many more risk factors. But wouldn't it be nice if we could rule out at least training errors and these everyday activities from our risk factors in order to better understand that? And one way to approach this problem is sensor footwear, which intends to use the information that is contained in the interaction between foot and the ground by using sensors attached to the foot. And these technologies have made rapid advancement recently due to improvements in microfabrication processes, wireless communication, and also sensor systems in general. Here you see some main application areas ranging from gait monitoring to forest applications. And here you see some pictures of products that are already available where the sensors are either integrated directly into the shoe or can be attached to the shoe or put in by means of insoles. But at least to my knowledge, they do not try to estimate the classical loading variables that we use and that we have had researched over the last decades. And therefore, the purpose was, in the very first approach, to explore the potential of sensor-equipped footwear to predict basic loading variables during constant straight running speed. And in this case, we used 3D accelerometry as an example. And therefore, we collected data from 221 runners, and we calculated lower extremity kinematics and kinetics. In particular, we used ground reaction forces and free moments using a force plate, but we also calculated 3D joint moments using standard inverse dynamics. But then we also extracted features from two markers attached to the, one marker attached to the heel and one marker attached to the first big toe. After filtering them with a 20 Hz low pass filter, we got positional data in 3D space, and we ascribed them in the rear foot coordinate system and in a forefoot mounted coordinate system in order to mimic the attachment of 3D acceleration sensors to footwear. Then we performed 2 times numerical differentiation to come from the position data to the acceleration signal, which we analyzed during the stance phase of running. And we did that for the anterior-posterior component, but also for the mediolateral and vertical component, which resulted in the end in 3 acceleration signal components. And then we extracted features during the stance phase, which were peak values, but also average values determined over 10% interval of stance, and also negative, positive, and net impulses. Which resulted in a total of 128 features for the rear foot and for the heel and the toe marker. But we also had anthropometric features, which were body height, body mass, age, and gender. And then we performed this statistical modeling or pattern recognition part, where we used our acceleration features to predict the response variables, which were the loading variables of interest. And therefore we used the so-called least absolute shrinkage and selection operator, or in short, LASSO. And that in the end means that we had one model for all runners per loading variable. What the LASSO does is that it's minimizing the following formula, which basically consists of a standard residual sum of squares part that is least squares fit, known from typical multiple regression analysis. But it also adds a penalty term, which penalizes to have a big amount of non-zero model coefficients or predictor variables in your model. The LASSO is known to be very good in reducing the number of predictors in the multiple regression model, and it's also well suited for wide data set. Wide meaning that you have relatively few participants, but a great amount of predictor variables. And has been shown to be good in identifying important predictors and in selecting among redundant predictors, which makes it a powerful tool for model selection and dimensional reduction in regression modeling. So in short, I'd like to summarize the methods. First, we had the data collection, then we were calculating the loading variables, extracted the acceleration features, performed the LASSO model fitting, and then in the last step, we evaluated the prediction performance using Van Latten plots and 95% limits of agreement. Come to the result. Here you see the Van Latten plots for a relatively good prediction and for a relatively bad prediction, which was for the peak vertical force and the peak knee adduction moment. On the y-axis, there's plotted the differences between the predicted and measured values. And here in blue, the blue areas indicate the 95% limits of agreement, which means that 95% of the differences are found within that range. And in this table, I've summarized all of the results of the study. So we have 11 loading variables that I tried to predict. And in general, we found that if you add more predictor signals or more predictor features in the modeling part, then this improves prediction performance. Because you have in the first column the prediction which is based only on the anthropometric data, then prediction based only on the heel acceleration signals, only on the toe acceleration signals, and then in the right column we use all features to predict the loading variables. What we also found was that there is a better prediction performance for parameters within the sagittal plane, like peak ground action forces in the sagittal plane, but also peak ankle and knee joint moments in the sagittal plane. But still, we must admit, if we look at the numbers, that the overall prediction performance is pretty weak. The only more or less acceptable value might be found for peak vertical force, while the limits of agreement are definitely too high for all the other parameters. Still, in summary, I feel that there is at least some evidence that the prediction-based estimation of loading parameters based on machine learning algorithms might be feasible, even though when using only acceleration signals, the performance is, using our method, insufficient. But it could be improved by using more sensors or different sensor technology like gyros or pressure sensors. Or you could also use more sophisticated machine learning or pattern recognition algorithms. Then you have to consider that there's always a trade-off between precision and computational or battery costs. And for research purposes, I think that there could be improvements when not using an overall model fitted to all participants, but by using individualized model for each subject. And that could be, a good approach for research purposes. For example, if you want to perform a longitudinal study. Thank you for your attention, and I'm looking forward to your questions.
Julie Still, Wollongong University. Thanks, Vikas, for a lovely presentation. I may have misinterpreted, but you were using ground reaction force data and moments and that to then predict in the regression. Okay, so I did that wrong. Because aren't they related? We can't use them on regression related variables or variables from the same source.
I actually mean that if the predictor are correlated, that's possible. I think you can still use that because essentially if you use a model you have lots of I think that is if you want to get insight from a model, then it's a problem because then you can't really rely on the coefficients that you get and you can't really interpret them. And if you just use it for prediction because you're interested in getting to know your loading variables outside of the lab, then I think it's feasible to use that. Because the method in itself finds a certain set of variables and also includes rotation points. So I think multicollinearity is not the issue that you see.
Frederick Calgary, could you give me a functional reason why the accelerations of the heel or the forefoot could be related to general body loading? You know, I would have speculated they are not. Why did you speculate they are?
I think there is some evidence in the literature to suggest that accelerations of body parts can relate to acceleration. I agree that only using the foot is maybe not sufficient in order to have the overall body component, but I think the research done by Peter Wang's group, and I think it was shown that at least some portion of the acceleration is determined by the foot acceleration, and also contained in the AP component of the acceleration is information regarding to the velocity of the runner, because you simply move your feet faster then. And the velocity is strongly correlated to the height of the vertical component. So I think there you find the information. But still, the prediction performance is relatively poor, and adding an accelerometer to the lip, for example, might improve the results. But I would go a different direction. I would maybe use pressure insoles and use that information in order to further improve it, because I think part of your doubts is the reason why the prediction performance is so poor at the moment.
The method is very interesting, and perhaps with different signals it might be more powerful. But I'm also curious, in your attempt to do this, you use accelerations derived from the motion capture. You filter the motion capture data and then differentiated it twice. That would, I would imagine, effectively introduce a distortion in those acceleration signals, and it isn't necessarily the most realistic representation of the actual acceleration signals you would have thought being actually used. Have you done any investigation to see how the acceleration signals you were using derived from motion capture data compared to what would have come from the instrument token.
I understand your doubts, and what I did was putting a marker on a 3D accelerometer and compare the signals, and you have to make sure that the orientation of the coordinate system is the same, which is quite difficult to do. So what I ended up was rotating the acceleration signal until they matched. And then it's also very important how you filter the acceleration signals. So I think you can't really compare the two approaches if you're using raw signals, but if you find correct filter coefficients for the acceleration signals, then those two signals become very good.
Thanks for the talk. Let's move on to the next question. The next presentation is by Daniel Costa, and his presentation is on the reproducibility of wearable kinematics, measuring the inertial sensors within outdoor running on different surfaces.
Thank you for the introduction. I'm actually replacing my colleague Yasmin for her good knowledge because she did most of the work in the study. So I want to just briefly talk about the background of the study. In our opinion, one of the problems in the investigation of running movement is that the majority of the studies is performed in a laboratory situation. And it is questionable whether within a laboratory setup, a runner, if we just collect a few strides or we record traffic runs, will develop a more natural stride rhythm. This is why we believe we need alternative approaches to investigate runners, possibly in their natural running habits, so this would be outdoors, and an alternative device that will help us or allow us to do that are inertial sensors, because they allow us to describe all 6 degrees of freedom without any special restrictions they are given to, for instance, camera systems. They are also lightweight, they're relatively small in size, and they have low power energy consumption, so this is why they're more suitable for outdoor testing. However, whenever we want to use new measurement devices, we want to make sure that they are adequately reliable and valid. So this is the focus of the study, to investigate the reliability of inertial sensors, especially with regards to the use in the running. There have only been a few studies who investigated particularly the reliability of IMU running. For spatial temporal parameters, good reliability could be established, but only for walking days. On the other hand, for outdoor and treadmill running, a rather large variance was reported for inversion velocity by 2 studies from our research group. So the purpose of this study was to investigate whether or not spatial temporal and kinematic graphic parameters are actually reproducible in outdoor running on different surfaces and between different measurement day intervals. For the study, we tested 22 well-trained runners. They were obviously running outdoors. Before they started to run, they decided to run on an uneven surface, which 15 of the participants did, or on asphalt, which I will refer to as even surface, just based on their usual running habits and preferences. We tested on 3 different measurement days, with 1 week between the first and second measurement day and 3 weeks between the second and third measurement. We asked the participants to run 45 minutes at a self-selected speed. And to make sure that the speed was constant, we excluded all trials that exceeded a maximum variation of more than plus minus 1 kilometer per hour. We recorded data using an inertial sensor unit that we placed on the left heel cap. The sensor unit consisted of a 3D accelerometer as well as a 3D gyroscope, both measuring at 400 Hz. Regarding the data processing, we extracted 2,000 strides from the middle of the run, and for each stride we calculated the stride duration as well as the maximum inversion velocity to check for systematic and possible interaction effects. We ran a two-way repeated measures ANOVA with attractive surface type and measurement date. And to investigate reliability, we determined mean differences, also referred to as bias, to describe systematic error and limits of agreement, as well as root mean square error, all absolute and relative to the mean. And this graphic shows mean values indicated by the circles, as well as standard deviations shown by the vertical lines for all 22 subjects over 2,000 strides. We can see that the standard deviations are actually pretty similar between the measurement days and also for both surface conditions. Also, we didn't find any significant differences between the two surface conditions and no interaction effects between surface condition and the measurement day. For inversion velocity, however, we did find an interaction effect between the surface condition and the measurement day, basically meaning that there was a difference between the first and third measurement day with regard to which surface the runners ran. The following I will show Bland and Altman plots for the differences between the measurement days. We'll start with the strike duration. So on the x-axis of the Bland and Altman plots, you can see the mean values, in this case for the strike duration, and on the y-axis you can see the differences between the measurement days. You also can see the absolute values for bias and limits of agreement, as well as a table showing the relative error. For strike duration, error is generally relatively small across all three measurement days. I'm going to go through this rather quickly. So, for like differences between the first and second and third, as well as the first and third, we always found relatively small errors, like a maximum error of 1%. For the inversion velocity, because we found these interaction effects, just for the purpose of this presentation, we put it into one plot. But since there were differences between the surface conditions, we marked limits of agreement and the bias with different colors. So for the uneven surface, it's light in blue, and for the asphalt condition, it's in black. So for the difference between the first two measurement days, we see there actually was a pretty small error for the inversion velocity. However, with increased time between the measurements, so this is just 1 week in between the measurements, but if we go further, and there were 3 weeks in between the measurements, the measurement error interestingly increased, and there were differences between the surfaces. A similar pattern was found for the differences between the first and third measurement day. Regarding the reproducibility of the parameters, for both parameters we found similar effects for both surface conditions. And the random measurement deviations between repeated measurements were about 4% for strike duration and up to 20% for the inversion velocity. To sum it up, strike duration turned out as predicted to be a more reliable parameter, so the measurement error seemed not to be influenced by the surface condition or the time between the measurement days. For the inversion velocity, interestingly, the reliability decreased with more time in between the measurement days. And the differences between those measurement days seem to depend on the respective surface condition. Even though these effects were significant, they were still rather small. And I also have to highlight that the sample sizes between the groups were not the same, so we had less runs for the even surface condition. This might have affected the outcome. Overall, the deviations that we found were similar to the previous studies I mentioned for both treadmill and outdoor running. So the spatial temporal parameter turned out to be more reliable than the kinematic parameter inversion velocity. With regard to the overall random error, inversion velocity seems to be highly sensitive to all kinds of internal and external factors, changes. This could be anything from fatigue effects to foot placement, the way we mount the sensor. What we could not explain within the course of this study was the reason for the systematic error that we observed between the measurement days. Thank you for your attention.
Thank you very much, David. This question is now open for questions. One over the other day.
Good information, thank you. I apologize if I missed this, but can you give us more detail about how you determine your spatial temporal parameters?
Yeah, sure. So you mean like the way to determine the
Yeah,
size?
what data you extract from the unused accelerometer or gyroscope, or?
It's not like I was expecting that question, but like my supervisor, Christian Meyer, 2 years ago, maybe even the strike detection algorithm based on gyroscope signals that the Lopez filter to get so like almost like a sinus-like curve, and within these curves, he detects acceleration peaks that are used as the actual ground contact times. And we worked with this algorithm in a few studies now, and it always seems to work accurately, also compared to mocap signals in other contexts. So if you want, you can just talk to me later on. I can tell you how the paper is called, something with strike detection.
Any more questions that we already have slides for? I've got one that's maybe more a comment than a question. You had smaller standard deviations and also better reproducibility on the uneven surface, if I understood it right. I was just looking at the graph where you had all the different days, and the standard deviations were pretty consistent and quite small, whereas for the even surface they seem to be a bit bigger. And I think one of the reasons why we often run on even surfaces in the laboratory is to have standardized conditions, so it seems like the uneven surface might have, in a way, more standard results with the even graphite. So I'm not sure if you can answer that, but it's an interesting phenomenon.
I actually thought the same, but I don't really explanation to be honest.
There are no more questions. I'd like to take out again to my presentation. I'd like to ask any viewer to come up and present the next talk. Wrong perspective. And the talk will be on the establishment of the estimated technique for joint load input range.
Thank you, Chair. Hello, everyone. I'm Aya Mura. Today, I'd like to talk about the estimated technique for joint load input during learning by using three-dimensional ground reaction force distribution. Let me introduce my study. Recently, long-distance learning is getting a popular leisure with health conscious and the popularity of learning events. Meanwhile, it has been said that the risk of lower extremity injuries are increased during long-distance learning. For example, there are tibial and metatarsal bone stress fractures. Namely, reducing repeated loads are important. As a precaution, cushioning is required in learning shoes. Certainly, this is one solution, but are there any options? To answer this question, we need to know the injury mechanism. However, the injury mechanisms such as bone stress fractures have not been clarified yet. One of the reasons is that the load input couldn't be estimated in detail, I think. In previous studies, Two measurement methods are mainly used for estimation. One is frontal pressure distribution and other is ground reaction force. In frontal pressure distribution, it can be obtained only specific vertical pressure distribution, but no horizontal one. On the other hand, in ground reaction force, it can be obtained accurate three-dimensional force, but no distributions. So, to estimate the load input in detail, three-dimensional ground reaction force distribution between foot and surface need to be considered. So, the purpose of this study is to establish an estimated method for joint load in foot during learning. 3D force distribution was measured by using special shoes with miniature sensor force sensor as shown below, and the joint load torque were estimated by new simplified model with 3D force distribution on foot planter. Next, I'll explain measurement method. We conducted the experiment to obtain the data, which was input to the foot model. A subject ran with the shoes, mounted miniature sensor, and 3D plantar force distribution were measured during stance phase of learning. And at the same time, ground reaction force and 3D coordinate of foot segments were measured by the motion capture system. This is a proposed model. In order to estimate joint torque in foot, a simplified foot model were defined as link segment model. This model composed of two mid-foot and heel part region and joints which linked each segment was equivalent with LV joint, TM joint, and ankle joint respectively. Each joint torque was estimated as follows. First, the joint torque components tau were obtained from 3D forces of sensors, and joint torque was calculated by sum of torque components respectively. For instance, if the load input to sensor 18 like this, joint reaction forces work on each segment. And third, torque components can be calculated by inverse dynamics. In case of TM joint torque, if this calculation flow conducted, we can get the history of torque components during stance phase. This is sensor 18. And by using same procedure, torque components at sensor 9 to 19, it can be shown like this. Positions will contribute to joint torque as changing from here to 2. And next, these torque components were summed up. TM joint torque can be shown like this. And torque calculated by conventional method is shown. Both torque are fit from 76 to 100 of stance weight. And torque by sensor rises up at 10%. On the other hand, torque by force brake rises at 35%. Namely, TM joint torque components can't be estimated by force brake at early stance weight. Next, this slide shows the time history of torque components at each sensor position. Green and yellow lines show horizontal and vertical torque components respectively. And blue line shows the total torque components. In comparison of horizontal torque component histories, components under LP joint increased by 80% of stance weight. On the other hand, the vertical torque component is same trend with total torque component. As described above, anchor, TM, and MP joint torque historical distribution were able to be shown like this. Here, by using proposed model, each joint torque distribution is quantified. Here are some of the results. By using proposed method, TM and MP joint torque could be estimated through stance weight, and each joint torque component in foot could be detected. So we think, given torque components, it is expected that bone stress may be clarified and solid reduced injury risk will be defined. From now, for example, I discussed MP metatarsal bone stress. A joint composed of multi-bones, and we think TM joint torque was probably related with metatarsal bones. So it is assumed that sensor position arrangement is corresponding to each bone, as shown color-coded, lateral center, medial center, and lateral lobe. This result shows the total torque component of each lobe, and left picture shows the torque components distribution at the peak. The center lobe is higher than the others. The center lobe is supposed to be corresponding to second and third metatarsal bones. So this result is good agreement with the previous report, which reported metatarsal stress fractures linked in long distance running occur on mainly second and third metatarsal bones. And here, how can we improve the shoot to prevent the injury? I'd like to explain the possibility that the sole thickness distribution may reduce the stress of metatarsal bones. This is an example. A spacer was inserted under small ball like this, and we conducted the same test. The top picture shows the comparison of torque components at the peak between normal and spacer condition, and the bottom graph shows the total torque components of center lobe highlighted red, and the peak torque of spacer is decreased from normal condition. So it may suggest that the stress of second and third metatarsal bone might be reduced by sole structure design. This is the final slide. I'd like to conclude my presentation. I believe the proposed technique to estimate foot joint torque helps the functional sole design, and through this process, I'd like to continue to create this functional shoes which can express not only injury prevention but also running economy. Thank you for your kind attention.
うちはやってないですね。課題は100台ぐらい入れてますけど、じゃあ手首杯やってます。センサーは住友リモートやってますけど。
Polismo from the University of Target. You showed some differences in the moment for the TM joint. Did you ever look at the difference in the ankle joint torque between your new method and the traditional method, and were they more similar?
Yeah, now I showed the TM joint result only, but the same point shows in ankle or MP joint torque.
So there was a similar difference, or the torques were similar at the ankle joint?
Yes. Similar joint, so not so big difference.
Any other comments? Thanks, Neera, for the great announcement. Okay, the next presentation number 6, is by Alessandro Bartolini from Victoria University, Melbourne, Australia. And his presentation is on food strike classification and comparison methodologies.
I'm not Italian, so I'm Alessandro, supervisor. So I've snuck in here last session. Okay, so this study asking the question of the importance of classifying foot strike technique in runners, because it's important for classifying group membership of participants, and a lot of studies investigating injury have been related to the type of foot strike at the onset of foot contact when running. And it's also important to be able to understand the impact problem. So that is the initial condition at landing and what effect that has on the locomotor controller in terms of it finding a movement solution to that initial condition. And so, simple spring mass model illustrating the problem of impact that needs to be solved, and that can be solved either from a perspective of the changing momentum of the body centre of mass, or it could be investigated from a change in energy perspective. And so either perspective is either looking at it from the force time perspective or the force distance perspective. And lots of studies have been investigating the curve here and looking at loading rate, looking at how in nature animals are able to smooth out the ground reaction force curve. But in humans and in running shoes, the challenge is being able to run and have a smooth ground reaction force curve. So there's different strategies that a person can adopt when landing. With a rear foot strike, they would use some type of a dorsiflexor power absorption strategy to control the impact. Or they could have a plantar flexor power absorption strategy in the deformation or the change in limb length of the limb and changing the position of body centre of mass at impact. So depending on the type of foot strike will indicate to the controller what type of strategy they will adopt to control this problem. So traditional methods of classifying foot strike is foot strike index, and the diagram on the right is the foot strike index first proposed by Kavanagh and Fortune many years ago, just partitioning the foot into thirds, and foot strike classification was based on that proportion. And the other method employed, foot strike angle, so foot progression angle at impact, and just looking at sagittal plane, and a lot of the studies would either zero the foot progression angle during stance and use that as a reference. There's been two studies highlighted here that have used some other values to determine whether it's a rear foot strike or a forefoot strike. Sometimes this might seem arbitrary. Altman and Davis, they had a method that justified why they would choose those values of negative 1.5 degrees as a forefoot strike, and greater than 8 degrees of dorsiflexion as a rear foot strike, because they related it to the foot strike index. So the purpose of this study was to evaluate foot strike classification methods and to propose some new methods. One in particular is that it has a functional measure and that it can capture what the controller might be able to be paying attention to, and that is the ankle angular impulse during the impact phase, and to compare these to the traditional parameters of foot strike. And whether these parameters can explain the variance of control variables or proposed control variables of running. So we used a group of athletes that, elite athletes that run in conventional footwear, and they also compete in footwear that is of a minimal type of shoe. So we had 30 participants. So they ran over ground on in the lab, and we collected 3D motion analysis data over a force platform, and we measured body center of mass position, ground reaction forces, and 3D limb kinematics. So, messy slide here, but on the left, these were the proposed control parameters, and the loading rate being one of those proposed control parameters at impact. The other proposed one is limb stiffness, which is, so we described the average loading rate as close to an instantaneous loading rate, but it was from 0.2 body weights to 1 times body weight, so it was a small proportion of the impact phase, and limb stiffness was a conventional way of describing that control parameter, and that was just the change in limb length, the resultant limb length, and the change in the resultant ground reaction force. We looked at other proposed foot strike parameters. One is the ankle joint moment, and that was just the moment that was present at initial contact. And the second proposed was the ankle angular impulse. So this messy equation is just essentially the area under the ankle moment curve, and we summed the positive and negative proportion of that curve, and we normalised it to the total absolute area under the curve. And so we termed that the ankle angular impulse, and if that impulse was less than negative 50, which was a proportionate value, then we describe that as a rear foot strike. Foot strike angle, there's methods in the literature that will use just a zero reference, and that's a reference to the stance position of the foot. So whatever the foot coordinate system is during stance is zero. There's other, we took a value here of 5.9 degrees that someone had proposed by, that was by Lieberman. And we used a foot strike index based on an anatomical index. So we used the ankle joint center and the metatarsophalangeal joint center as a new foot strike index. So from the classification, these were the proportion of our cases that were in the rear foot strike classified. So if we used a 0 degree foot strike angle, we had 85% of our cases described as a rear foot strike, whereas if we used a 5.6 degree value, we had 53%. And on the right, we've got the forefoot strike, and in brackets is the midfoot strike values. The last row is the ankle angular impulse, and that was 46% were midfoot strikers in that case. So there's some differences there. We used a McNeema square test, and this was the significant change when classifying the change in group based on the variable. And so we see significant change based on if we were using a foot strike angle of 0 degrees compared to the functional method, which was the angular impulse. And so that was our reference. And so there are two significant changes or differences between the functional method of classification, and that is the 0 reference and the foot strike index by Kavanagh. So this was a study several years ago, and it suggested here that there's a linear relationship between foot strike index and foot strike angle. And so here's rear foot strike, mid foot strike, and forefoot strike. They're all shod conditions and a barefoot strike condition. And so that was able to explain the variance quite well. But there was some spread down this quadrant here with the rear foot strike. This is data from our sample, and we see a strong non-linear relationship between these two variables. So what we see is 600 foot strikes, and there's a non-linear relationship here. So this is a discrepancy. There are some similarities, but where we have some differences is where we've got low foot strike index, and we get a strong linear regression here that's able to explain some of the variance, but that is when we partition these results according to the foot strike pattern and the footwear condition. So this graph here shows the foot strike angle classification and how it relates to the body, the loading rate. So the loading rate is the vertical axis here, and foot strike angle is the horizontal axis, and they're the different footwear conditions. So the forefoot strike group is the blue, and the forefoot strike shod is the black. But we get here a good linear relationship, but that's only when we separate the groups. We relate foot strike angle to the other proposed control parameters. So it might be the control of the limb length displacement, or it could be the limb stiffness. We see that the categorization has a great spread. And if we were to use the foot strike index against some of those proposed control variables, again there's more difficulty in that relationship. So we do a non-linear regression, and we're able to explain the relationship between foot strike angle and the loading rate, and we see that there is a maximum at around about 6 degrees of dorsiflexion. So at 6 degrees of dorsiflexion, and that relates to a loading rate of 241 body weight per second. So this nonlinear regression explains 41% of the variance. Another interesting finding was at 6 degrees at that same foot strike angle, this was the least frequent foot strike angle adopted by our 600 footfalls. So this looks like it's a foot strike angle to be avoided, and it seems like it's to be avoided because it's associated with large loading rate values. So the takeaway is a nonlinear relationship between foot strike angle and foot strike index. These classification methods, when selecting a foot strike angle of around 6 degrees, dorsiflexion, or using a foot strike index based on an anatomical reference, which is using the ankle or metatarsophalangeal joint, is more closely related to functional measures of impact and more closely related to the ankle angle impulse. Foot strike angles are around 6 degrees were associated with the highest loading rates, and foot strike angles of around 6 degrees were least frequent when we explored this cohort. Okay, thank you to these supporters, and thank you for listening.
Nice talk and nice method. The paper is open for maybe